Hello and welcome to this clip looking at electrode potentials and equilibria together. I want to focus on how you can include both in your answer wording when directed to do so. So I've taken the electrode potential data from one part of the question and the relevant questions section, which tells you what to do with it, from another part of the question. There were clearly some other bits that the whole question was asking you to do, so I've pulled two bits together that are relevant so you can see them all in one place. So let's start with the electrode potentials. It tells you that zinc reacts with acidified Cr2O7 to form Cr2 in two stages. So you've got to find the half equations containing these species and compare their electrode potential values. So I'm going to get rid of the ones that are not relevant and stick to the ones that are. So now you can visualize what it is you're dealing with. So let's do it stage at a time. The first stage is the zinc and dichromate. So if you take the electrode potential values, you can see that the electrode potential value for zinc is more negative than that for dichromate. So at this point, we need to switch to talking about equilibria. So you can see that there's an equilibrium sign in all of the half equations. So that means they can be treated as equilibria. Normally, when we do electrode potentials, we might say things like the more negative electrode potential, or the half equation with the more negative electrode potential is reversed, or it proceeds as an oxidation, or such like. But you can also say the position of equilibrium shifts to the left. So in this case, that's going to be the zinc half equation, whilst the position of equilibrium for dichromate shifts to the right. So the idea here is down at the bottom in pink. The half equation proceeding as a reduction will have the POE shift to the right, and vice versa. Then they want you to include overall reactions, or overall equations for the reactions which actually occur. So looking at the zinc, we know that this one is reversed, but looking at the electrons, there's 2 electrons transferred. But if you look at the dichromate, there are 6 electrons transferred, so you have to multiply the zinc half cell by 3. And keep the dichromate one the same. So doing this gives us 3 zincs, 1 dichromate, 14 H pluses, giving 3 Zn2 pluses, 2 Cr3 pluses, and 7 waters. So next we turn our attention to the Cr2 plus and find the half equation that contains that. So again, the electrode potential value for zinc is more negative at minus 0.76 than the electrode potential value for Cr3 plus at minus 0.42. So once more, the position of equilibrium for zinc shifts to the left, whilst the position of equilibrium for Cr3 plus shifts to the right. So this time the zinc has 2 electrons, but the chromium 3 plus only has 1. So you have to double that so you can cancel the electrons, which allows you to write zinc plus 2 Cr3 plus, giving you Zn2 plus 2 Cr2 plus. So now let's look at the question as it was actually presented and put in the different parts that we've just worked out. So the first pairing, those are the things that we came up with. And the second pairing in stage 2, these are the things we come up with. So what's the technique for writing this? Well, first of all, you compare the E values, the electrode potential values. Then as a result of that, you can state the equilibrium shift. And finally, you do the overall equation by cancelling the electrons, multiplying up where necessary. So before we finish, let's have a quick look at the mark scheme. So there's different ways in which you can get all 4 marks. And in the guidance, you can see it's quite lenient. So you don't bother with lower or higher. You have to say more negative or less positive. It's important use of language there. Okay, thanks for listening. Until next time, see you soon.